Proof 2, consider n possible positions for the n objects. Okay. So there are identical objects. I'm not going to relabel them or anything, right? So out of the n positions, I choose n1 positions to put the type 1 object. Okay. The type 1 object can appear. They are all identical, right? So no matter, I don't want to look at the order. So I want to just form a subset, right? Say that, okay, these are the guys who are going to appear. And where are they going to appear? In the n1 positions, wherever positions and I'm going to take. So I choose the n1 positions and say that, okay, I just put all the copies of this object in this particular positions. So how many ways I can choose the n1 positions? There are n positions available. N choose n1 ways I can choose the n1 positions, right? So I fix the n1 positions for the first object in n choose n1 ways. So I selected this. That positions are not available anymore, right? So once I have removed this n1 positions and put the type 1 object there, I look at the remaining n minus n1 positions, and out of this I choose n2 other positions, right? These n2 positions I will put the type 2 object. They are identical. I don't care which order. I just put them there. So continue this way. I choose n minus n1 minus n2 minus etc. nk minus 1. Choose nk ways. I can choose the nkth type object, right? Nk position for the last object, right? So each object I choose. Now these choices are independent because the position that we are selecting were all distinct, right? So I selected the first n1. The number of choices were independent, right? Because first n1 I select. Now I remove this, and then from the remaining n minus n, I am choosing n2 position. So therefore, that choice, the number of the choice is only depending on how many are remaining, which is n minus n1, right? So that n2 positions choice is the same always, and they are independent. So therefore, I can multiply, right? I can first fix this guy and then multiply this, then I can multiply this, etc. Now this product is precisely finding the number of ways to arrange the terms, right? In the multi-set, I'm going to arrange the linear arrangements of the objects, and that is I can obtain in this way. So therefore, this thing must be equal to what we were counting, right? So this is going to be equal to n factorial by n1 factorial etc. nk factorial. So show this equality. You can use algebra, right? If you want algebraic method. Combinatorially, there is nothing to say, right? They are equal because the combinatorial proof is clear because we just did the same thing, right? We selected or we just basically counted the same object, right? We counted the number of possible ways to form words or to arrange objects where there were n1 objects of type, n2 objects of another type, etc., nk objects of another type, and that we found to be this in one counting, and we found it to be this in another counting, and therefore these two things must be equal. So there is a notation for this, which is n choose n1 comma n2 comma etc. comma nk. Okay, this is called the multinomial coefficient, as I told you earlier. So the notation for multinomial coefficient is n choose n1 n2 etc. nk, and that is equal to n factorial by n1 factorial etc. nk factorial. And I want you to show this as a homework. Why this product must be equal to this factor, right? N factorial. This is a closed form. This is a product. So find it out. Okay. And it's very easy. One example. Okay. So any theory we look at least some examples. So consider an 8 cross 8 chessboard in which we place 8 rooks so that they cannot attack each other. So how many possible ways are there to keep the rooks so that they cannot attack each other? So if you are not familiar with chess and rooks, I will tell you how the rook moves at least and attacks. And as a addendum to the question, I can ask, okay, suppose the rooks are not the same color. Okay, we will first assume that all the rooks are identical, the same color. But then we can say that, okay, suppose one rook is blue color, two are white color, two is red, and three are yellow. Then how many ways we can do this? Will the number increases or decrease, whatever, right? So, so here is our chessboard. Okay, so chessboard is usually labeled with the ranks of the chessboard. It's called ranks, called A, B, C, D, E, F, G, H are the ranks. So the person will sit. The person with the white pieces will look. So here I am looking color and all, giving color and all, but don't worry about that. We'll sit here with this will be a white corner and this will be a white corner in the chessboard. And then this A, B, C, D, E, F, G, H will be written here where the person with the white color sits, and here the opposite side the person with the black color sits. And these are called ranks. Okay, so the when the pawn or something moves, so this which row it is, it's called the rank. Okay, 1, 2, 3, 4, etc. up to 8. And so these are called files and these are ranks. Okay, so now, so there are these objects called rooks which can move in the following way. Okay, a rook can move in either in its rank or along its file. Okay, at one movement it can just move in one direction. Okay, so it can move either this way or it can move this way wherever it is sitting. So this guy, for example, can move either this way or this way, or it can move here or it can move here. Okay, so yeah. Sorry. So first, discard this color that I have given to the rooks. Okay, the color was for the second part of the question. I don't want to do two times this. So I gave a color, but assume that all of them are of the same color for the time. Now we have these 8 rooks. Now, when 2 rooks are in the same rank or the same file, they can attack each other. Okay, because one can reach the other guy going in that direction. So therefore, if they are in the same rank, they can attack each other. If they are in the same file, then also they can attack each other. So I don't want the rooks to be attacking. So if I have a rook in this position, then I cannot put any rook here, anywhere here, or anywhere here. Similarly, so then I can put the rook in maybe here if you want, for example, right? But then again, if I put one here or here, whatever, then in this rank it cannot have, right? And this file it cannot have anything. So this way, I want to put 8 rooks so that they don't attack each other. So I want to count the number of ways I can do this, right? So how do you count this? Okay, again, think about this. Try to find your own counting, and then see whether the answer matches with what we do. So spend some time, and then if you are back, we continue. Okay, so what first we observe that because if I look at the ranks, let's say A, B, C, or the files A, B, C, D, etc. H, each file can contain at most one rook, right? Each file can contain at most one rook, right? Now, therefore, I number the things as follows. Okay, A comma J1. Right? The first rook wherever it is appearing in the first file, the A file in the J1th position. Okay, in the B file it can appear in the J2th position maybe, and in the H file it can appear in the J8 position. Okay, so I know that any of the 8 rooks must appear in 8 of these different files, so there is no choice in that, right? They must appear in 8 different files. They cannot appear in the same file. 2 of them cannot appear in the same file. Now, once I choose 8, these are the 8 files I have. So once I choose the 8 rooks, I have to decide what are going to be my J1, J2, etc. J8. Now J1, J2, etc. Can I have A J1 and B J2, where J1 is equal to J2? If J1 is equal to J2, both of these rooks are going to be in different files, but they are in the same rank, right? But they cannot be in the same rank. So J1 and J2 must be different. So I have J1 to J8, and out of this J1 to A8, it can be any distinct 8 numbers from 1 to 8, right? It must be the distinct numbers from 1 to 8. But that can appear in any order, right? Any order I can have. For example, in the A file, if I have the first position, then B file I cannot have the first position, but I can take the fourth position, right? For example, C file I can take the second position, etc. H file I can take the sixth position. So this is possible. Right? So therefore, all I have the choice is the choice of the 8 factorial permutations for the ranks. So which rank I am going to appear in the J1, J2, etc. J8 position is possible to choose. So therefore, 8 factorial choices are there. So we have exactly 8 factorial ways to 8 factorial ways to arrange the rooks. If all the rooks have the same color. Now what happens if they have different colors? Now suppose all of them have the same color. We said that there are 8 factorial possibilities. We want to find out what if some of them have, like, one rook is blue, 2 is white, 2 is red, and 3 is yellow. Then what you do? It turns out that it is easier if you look at another question and solve it first. Okay. Suppose all the 8 colors were different. Then you know how to count it, right? Because we have 8 factorial ways to arrange them. But now I can color the rooks in 8 factorial different possible ways, right? 8, because there are 8 colors appearing, right? So I have 8 factorial ways to choose the rooks, and then I have 8 factorial ways to color them. Therefore, 8 factorial into 8 factorial possibilities to distribute 8 different colored rooks on 8 different positions here in the chessboard without them attacking. Now, since I know that not all of them are of the same color, now I will use the multinomial coefficients, right? The idea from there, because I can say that, okay, all these 8 comes from these things, right? There is one object of color blue, the blue colored rook, there is one exactly, n1 is 1, then n2 is 2, n3 is 2, and n4 is 3. So 3 plus 2 plus 2 plus 1, which is 8. So I have the 8 rooks, but 1, 2, 2, and 3 are appearing. But they, one object is of the same type, so 1 factorial, 2 objects of the same type, 2 objects of another type, and 3 objects of another type. So therefore, I can divide by 1 factorial into 2 factorial into 2 factorial into 3 factorial. And this will be my answer for the number of rooks, number of ways to keep the rooks, where the colors are like 1 blue, 2 red, 2 yellow, and 3 green, whatever. Right? So that is the idea. So time for homework. Okay. So here are some of the homeworks. So we have a deck of 52 cards. I hope that all of you are familiar with playing cards. If not, a deck contains 4 suits, which is red colored hearts, okay, with the heart symbol, 13 of them. Then 13 diamonds, which are also red colored, 13 clubs, and 13 spades, and they are black. Now, of course, a suit, heart, for example, the 13 cards will have the labels like ace, A, 2, 3, 4, 5, etc., 10, and jack, J, queen q, and king k. Okay, so these are the 13 labels for the suits. So each one has all these numbers. Now, suppose if all cards of the same suit must be kept together, so we can shuffle the cards. So the 52 cards we shuffle them, but we can shuffle them, but we have to make sure that all cards of the same suits must be kept together. So then how many orderings are possible? How many distinct orderings are possible for the cards? You put in one stack, but then we order them in different ways. How many different ways we can do this? So this is your first homework. Then next question is that count the number of divisors of the numbers that we already saw some example like this. 10 raised to 10, second is 740, and third is 25 into 31 raised to 4 into 7 raised to 6. Third question, how many integers larger than let's say 10,000 have distinct digits and does not contain the digit 5 or 3? Sorry. Fourth question is that how many ways to select 5 boys and 5 girls and to keep them alternately around a round table? Sit them. They want to seat them. So you want to seat 5 girls and 5 boys, and there are 10 seats maybe. And then in this around the round table, you want to, but we want them to be sitting alternately. So how many different ways you can do that? So many of these questions you might need to use several of the principles that we have learned. Okay, you can do all of them with the principles that we have learned, but you might have to use a combination of them. Fifth question, a multiset can contain more than one occurrence of some elements. Right? We already saw multiset, but let's say that the multiset contains A, B, 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 1, 2, 3, 4. Okay, so A is appearing 3 times. I denote the multiset in the following way. If 3 is appearing, A is appearing 3 times, I write 3 dot A to say that A is appearing 3 times. Okay, B is appearing 3 times, I will write 3 dot B. And then 1, 2, 3, 4 is appearing only 1, so I will not write anything, just the numbers. So, so this set is representing precisely this set. Okay, just for later references, we might use this notation. So how many 3 element subsets it has? Okay, 3 element sub multisets it has. Okay, I allow multisets, but it must be subset of this. I cannot allow more than, let's say, more than 3B, for example, in any multi subset, or I cannot allow more than 1, 2, for example, right? Because 2 is pairing only once in the multiset. So subset also, sub multiset also can contain only one copy of 2. Okay, then 20 people stand in a queue in front of a counter to buy, let's say, a new book that is published by, let's say, Harry Potter. Sometime back it happened, maybe, right? So a new book is published, whatever some famous author has published. So when the book is released, people go stand in queue. At the time of the release, they will stand in queue to buy the books. So let's say that 20 people stand in a queue in front of a counter to buy a new book. Price of the book is, let us say, 100 rupees. Okay, so each book has price 100 rupees. There is only one book for sale. Now on the opening time, the sales counter, they usually, this is what most of the time in shops, right? Or like if you go to bus, for example, right? You enter a bus conductor in the morning, first trip, has no money with him, nothing, zero cash. If you don't have change, you are in trouble. You have to wait for the change. So similarly, the sales counter opens with no cash. So if exactly 10 people have, let's say, 100 rupees note with them, and the others have exactly 200 rupee notes with them. Okay, they come with 200 rupee notes. 10 of them come with 100 rupee notes. Now we don't know which guys have 100 rupee notes and which guys have 200, but we know that 10 of them has 100 rupees and 10 of them has 200 rupees. Now what is the probability that, so the queue is arbitrary, right? People will come and stand there. Some of them have 100 and some of them have 200. What is the probability that no one has to wait for change, right? If somebody gave a 200 and then the clerk does not have change, cashier does not have change, he will say that, okay, wait there till I get the next guy or somebody who has 100 rupee. When he buys, I will give you the change. So what is the probability that no one has to wait for change? Okay, so find it though, it's going to be interesting. And seventh question, the sequence, we have, in calculus, we have already seen the sequence n by n plus 1 whole raised to n, okay, n greater than or equal to 1, is monotone, decreasing, and converges to 1 by e from basic calculus course that we have studied, okay. Now, prove that n factorial is greater than n by r whole raised to n for every n greater than or equal to 1 and r strictly greater than e, okay. So, e is the base of the natural logarithms. The next question, find a closed form expression for the given expression summation k is equal to 0 to n choose k, 3 raised to k, okay. And then next one is that summation k is equal to 1 to n, k by n raised to k times n choose k. So find closed form expression for these both of these using some of the techniques that we have learned.